Welcome to iLecture Online, and here we're going to look at capacitors placed in circuits, and circuits can be placed either in parallel, or the components in circuits can either be placed in parallel or in series. And what that means is if they're placed in parallel, they're placed side by side like this, which means that charges that will be pushed onto the capacitors can go on any one of the capacitors. So one charge can go here, there, there. They have a choice. So that's what we call in parallel. Another way of hooking up components in circuits is what we call in series, which means there's only one path. If a charge gets pushed onto this capacitor, it pushes a charge away from this plate, which goes on this capacitor, pushes a charge away from this plate, goes on that capacitor, and so forth. There's no choice here. All charges must go the same path. Here, charges can go into different paths. So this is called a parallel connection. And this is called a series connection. And then I put up a special case here, of course, that's also a parallel connection. There's only two capacitors, but again, the charges have a choice of which way they want to go. So this is also called a parallel connection. But here we only have two capacitors, and solving problems with only two capacitors in parallels, we have kind of special different methods for that. So I want to show how to do that as well. So bottom line, when capacitors are hooked up in parallel, it in effect increases the size of the plate. So however big this plate is, and however much this plate is, and however big this plate is, you can replace all three capacitors by a single capacitor that has the size of all three combined, which means that the total capacitance of the three is simply the sum of the three capacitors like that. And in this case, capacitor 1 is 10 microfarads, the second one is 20 microfarads, and the third one is 30 microfarads. You simply add them up together, and so the total capacitance of all three combined like that is equal to 60 microfarads. With other words, you could change the circuit into a single circuit with a single capacitor like that, that simply has a 60 microfarad capacitor. So these circuits, in essence, are similar to one another electrically. In series, it's a little bit different. In series, to find the total capacitance, you have to use this equation. 1 over C total, 1 over the total capacitance, is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So you add the inverses together, and then the sum of that, you take the inverse of that, and that gives you the total capacitance. So let's try that. So 1 over C total is equal to 1 over 10 microfarads plus 1 over 20 microfarads plus 1 over 30 microfarads. And of course, at this point, you can grab your calculator and work this out. But when you think about it, you can actually do that pretty well in your head. You can say that the common denominator would be 60 microfarads. So I'm going to multiply this by 6, this one by 3, and this one by 2. So 1 over C total is equal to 6 over 60 microfarads. I simply multiply both the top and the bottom, the numerator and denominator, by 6, plus 3 over 60 microfarads. I simply multiplied both the numerator and denominator by 3, and here plus 2 over 60 microfarads. That's simply multiplying the numerator and denominator by 2. Then adding 6, 3, and 2 together, you can say that 1 over C total is equal to 9 or 11 over 60 microfarads. And of course, when we solve for C total, we'll simply take the inverse of that, which means that C total is equal to 60 microfarads divided by 11. Of course, at that point, I'll grab my calculator real quick. And so 60 divided by 11 is 5.5 microfarads. There we go. So that's how you find the equivalent capacitance, the total capacitance with capacitor in series. And what that means is you can then take this circuit and simply replace it by a circuit with a single capacitor where the capacitance is equal to 5.5 microfarads, and this would have a very similar effect to the circuit as those three. You say, well, why would anyone ever bother making a circuit like this when you can make one like that? Well, there's different reasons why you use multiple capacitors, and we'll get into that later. Now let's take a look at the one where we have just two capacitors in parallel. Now we could use, oh wow, no, I don't want to show you that example. That's way too simple. Actually, what I wanted to show you is something like this. I want to show you two in series. So actually, 1 and 2. That's what I want to show you. So there's C1, there's C2. How do you find, and of course let me get a parallel right here. Actually what I wanted to show you is 2 capacitors in series. And again, you could find the total capacitance working out like this. You could say, well, 1 over C total is equal to 1 over C1 plus 1 over C2. But if you algebraically solve this equation for C total, you get C total is equal to the product of the 2 capacitors divided by the sum of the 2 capacitors. We call that the product over the sum equation. And that's a lot easier to work with. So looking at those 2 capacitors, this is equal to 8 microfarads times 12 microfarads divided by 8 microfarads plus 12 microfarads. And so this is equal to 8 times 12, that looks like 96. So we have 96 microfarads squared, because it's microfarads times microfarads, divided by 20 microfarads. And 96 divided by 20, well, that's almost 5. So that would be 4.16, that would be 4.8 microfarads. So you can see that when there's only 2 in series, it's a lot easier to use the product of the sum equation. If there's 3 or more in series, then you want to use this equation. And so that's how you work out capacitors in parallel and in series. Now, that's not the whole story, because now we're also going to take circuits like this and make them much more complicated. And then the question will be, how do you simplify, or how do you find the total or equivalent capacitance when you have combinations of these, where some are in parallel and some are in series? So let's do some examples where I can show you how to do problems like that. And then after that, we're also going to add batteries and put charges on these, and then you'll be asked to find how much charges in each capacitor, how much potential difference across each capacitor. So there's several more examples coming that show you how to deal with capacitors.